Welcome to the final lesson of the course R for Publication. Today we'll finish up going over a few final aspects of linear mixed effects models. For today's goals, we will learn about some other methods available when using linear mixed effects models, update our linear mixed effects models from the previous lesson, and now summarize our results in an R Markdown document. So part of the goal of this last two-part lesson has been to show you that linear mixed effects models can be an alternative to ANOVAs. However, you may still have some lingering doubts. For example, in an ANOVA, we got rid of our baseline issues. But can we do the same thing with linear mixed effects models? Indeed, we can. And actually, the method we'll use is not specific to linear mixed effects models, but can in fact be used with any kind of linear model. Let's start with the math. Once again, here is our data from Lesson 5 on US election results. As you may notice, the equation at the top is not for a linear mixed effects model, but just a simple linear model. All of the principles still apply, but I wanted to start with a simpler model as an example. In the past, we have discussed how in a linear model, when you have categorical independent variables, the levels are really converted into zeros and ones. So for example, the effective incumbent party is actually coded as a 0 for Democrat, the baseline level, and 1 for Republican, the non-baseline level. Similarly, the effect for Civil War country, Union gets coded as 0, the baseline level, and Confederacy as 1, the non-baseline level. As a result, the data for elections where Democratic incumbents and states in the Union is the data where both levels are the baseline, and thus the mean of that data is the intercept of the model, since the intercept is the value of y when all x's are set to 0. None of this should be new to you, but it's important that all this is clear before moving on. So this type of coding with one level set to 0 is called dummy coding. What we'll be doing is called contrast coding. Basically, with contrast coding, we reset the 0 value. So instead of it being a level of a variable, it's directly in between the two levels, in effect changing our figure to look something like this. What we've done is change our values for the levels of each factor from 0 and 1 to negative 0.5 and 0.5. So now the intercept, or the value of y when all x's are 0, is the grand mean of the data. If this is confusing right now, that's fine. We're going to go over this again a little more slowly. Let's say we're looking only at the effect of Civil War country. So now we're collapsing across incumbent party and just using a model with one variable. With the default coding of dummy coding, we get something like this, where 0 is Union and 1 is Confederacy. However, with contrast coding, we get something like this, where Union is negative 0.5 and Confederacy is 0.5. For both of these, we can still compute a slope between the two levels. In our dummy coded model, this slope is the value of b, as 1 minus 0 is 1, and b is the change in y for one change in x. Similarly, in our contrast-coded model, the slope is also b, as 0.5 minus negative 0.5 is also 1. So we're still looking at a change in 1 for x. As a result, these two models will have the exact same value for b, or the slope of x. Okay, but what about the intercept? This is where things start to get different. In dummy coding, the intercept is the value of y when x is 0. And in this case, x being 0 means x is the baseline category. So the intercept is the mean of the baseline level. For contrast coding, the intercept is still the value of y when x is 0, but now x being 0 is actually the mean of the two levels, since it's the predicted value in between the two levels, i.e. when x is 0. Take a moment and pause the video to look at this comparison to make sure it's clear. Now returning to our full example, our intercept is the value of y when both x's are set to 0. As a result, it's the grand mean of all the data. This also means that when we interpret our b's, or our slopes, they are in reference to all the data, not just the baseline level of the other variable. So it's giving us the same kind of information as an ANOVA. Okay, let's move to the R code. The equation for the model hasn't actually changed. We've just changed how we coded the fixed effects. I'll go into how to actually do that in more detail in the lab. Similarly, our equation in R looks pretty much identical. The main difference being the fixed effects now have underscore contrast after them. That's because I made a new column with the contrast-coded versions of the fixed effects. Otherwise, everything is the same. Let's move now to the model results. Again, our output looks the same in terms of structure as last time, but to really see the differences, let's compare our model with dummy coding and our model with contrast coding. Here's our dummy coded model from the last lesson, and here is our new contrast coded model. Let's start by focusing on the estimates for the intercept and the main effects. As you can see, they are different across the two models. Starting with the intercept, in the first model, that is the mean given our two baselines. But in the contrast-coded model, that is the mean across all the data, regardless of baselines. We also get very different looking numbers for our fixed effects. That's because in the dummy-coded model, our fixed effects are only on a subset of the data, given the other variable's baseline. But in the contrast-coded model, the fixed effects are collapsed across all levels of the other variable. Now let's take a look at the interaction. The values for the interaction are basically identical across the two models. Because for the interaction, the same comparison is being made. Changing coding to contrast coding should only change the estimates that are affected by baselines, which the interaction is not. Okay, we've now taken care of our baseline issue, but one final lingering question may be, how do I get p-values out of this? Recently, there's been an attempt to get away from p-values in science, but a lot of people still like them, so it would be better if we could get some concrete p-values to pull out of these models. This brings us to part 2 of our math. I'm going to take a quick break from talking about mixed effects models and look at some simple regressions. Here is some fake data I've generated that has a positive slope. As x increases, so does y. Here is another set of data, but as you can see, it's much messier than our first data set. If we were to draw a regression line for the first data set, it would look something like this. And for our second data set, the line would look like this. These lines should look similar to you, and indeed, they are identical. Both data sets have the same slope. But these are still very clearly different data sets. To describe this difference, we can talk about fit. Fit can be used to describe how close the individual data points are to your extrapolated line. And thus, we'd say that the first data set has a very good fit to the line, while the second data set has not such a good fit to the line. So what does this have to do with getting p-values for linear mixed effects models? Well, we're going to test how well our variables fit the data, and furthermore, to see if they fit it so well that they significantly improve the model, giving it a better fit, or if removing the variable doesn't significantly change the fit of the data. We do this via model comparison. Let's move to the R code. Once again, our equation has not changed, and here is our LMER call. As you can see, the only change is this REML equals false. This is a necessary addition if you're going to do model comparison for any LMER calls. However, it's not required for any GLMER calls. We're not going to stop with this model though. We're also going to build a second model that looks like this, which has accompanying R code that looks like this. The change in this model from the original one is that here we subtract our first fixed effect. Basically, we are building a model that includes the main effect of Civil War country and the interaction of incumbent party in Civil War country, but we're removing the effect of incumbent party from the model. As for the original model, we need the REML equals false call at the end. We now have our two models, one with our two main effects and the interaction, and one with one main effect and the interaction. So now we want to compare them to see if the full model, which includes the main effect of incumbent party, is a better fit than the model that removes incumbent party. To do this, all we have to do is run the ANOVA call. You just write the first model, comma, the second model. Running this will give you an output like this. There are several numbers here, but I'm only going to bring your attention to a few of them. AIC is one measure of how well the model is fit, and counterintuitively, a smaller AIC means a better fit. So when comparing these two models, the model M2 party the model without incumbent party, is actually a better fit of the data because it has a smaller AIC. You may also hear of people using BIC. I won't be going over the differences between the two, but the same principle applies. Lower value means better fit. This would suggest that including the main effect of incumbent party actually hurts the model. However, is this difference actually significant? To test this, the ANOVA call runs a likelihood ratio test, which gives us a chi-square value and a p-value. Here, the p-value is 0.6029, which suggests that the two models are not significantly different at a threshold of p less than 0.05. So, including the main effect of incumbent party does not significantly hurt or help the model. Let's go over the model comparison now for all three of our effects. First, we have the summary of the model itself, then the model comparison for incumbent party that we just went over, the model comparison for Civil War country, and finally, the model comparison for the interaction of incumbent party and Civil War country. As already discussed, if we look at the AIC and p-value for incumbent party, we do not get a significant difference between the two models. If we look at the original model, this makes sense, as we have a small estimate with a large standard error and a small t-value. Moving to the model comparison for Civil War country, again we get a slightly smaller AIC for the reduced model, the one without Civil War country, but our p-value suggests that any differences between the models are not significant. Looking back at the original model, again this is not surprising, given the estimate, standard error, and t-value. Finally, we have our results for the interaction. Here the AIC is smaller for the original full model that includes the interaction, and our p-value suggests the model with the interaction is indeed significantly a better fit of the data than the model without the interaction. This also matches our original model results, where we have a high estimate relative to the standard error and a high t-value. If you think back to Lesson 5, you may recall that this matches the results we got with the ANOVA. One thing to bear in mind, model comparison is useful for getting a p-value, but to know the direction and size of the effect, be sure to look at the estimates from the original model comparison. Now let's take the new skills we learned and come back to our lab from the first half of the lesson. All the data from the lab is the same as from part 1 of this lesson. We'll just be updating our statistics script to incorporate contrast coding and model comparison to get p-values for our effects. Pause the video now to do the lab. Come back to the video as suggested to learn more about the code in the lab. We start as we usually do by setting our old data frame to our to-be-created data frame. Next, we'll use a mutate call to create a new column. We'll call this column congruency contrast, since it's the contrast-coded version of the congruency column. To make this column, we'll use a conditional if-else statement based on the congruency column as the original variable, using con for congruent as our reference level. So for the first half of our if-else, looks for all the times that congruency is equal to con and gives it a new value of negative 0.5. Finally, to finish the if-else, we get the new value for incon, or when congruency does not equal con, setting it to 0.5. You can now continue with the lab. This marks the final video for the course R for Publication, and I hope that you enjoyed the course and found it useful. Best of luck to you in future R programming.